started. So we were here, right? We were here. I'm trying to explain the mapping scheme. So I drew CPU, cache, and main memory here. The same, figure, but rotate this figure 90-degree counterclockwise, right? So in this figure, I simplified. For simplicity, I don't want to write 32-bit address. So let's assume CPU is generating 8-bit address. Okay, 8-bit. I don't want to draw, 32 binary numbers. So 8-bit, and main memory is also small. Okay. Here we are assuming this is cache, right? Cache, and this is cache line. Cache line. Here we are assuming 8-byte cache line, okay, for simplicity. But reality, Intel, right? x86, 64-byte cache line, okay. That is a number the commercial processors are using. Right? Commercial processors has a 64-byte cache line. But in this example again, okay, for simplicity, we are using 8-byte cache line. Then main memory, right? Main memory is logically divided into this cache line sized blocks. Okay, so this each one, 8-byte, 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 right? So 8-byte, 8-byte. So I'm trying to explain the mapping. If cache miss happens, assuming that CPU, you are executing LW instruction, for example, right? 0x 5, right? So x0, right? That is better. You are executing that instruction, then you want to read the data from location 0, okay? And you search the cache first, but cache does not have anything at the beginning, so we have cache miss, right? Then somehow you have to bring in memory block. This one is called each one is called memory block, which is equal to cache line size. Cache, this one, right? Cache line size. Okay, memory block size, same cache line size, 8-byte, 8-byte. Okay, so cache miss happens. You need to bring in memory block to the cache. Then the question is, we have 8 entries, and entry number 0, 1, 2, entry number 7, 8 cache entries. So which entry you are going to use to place that memory block to? Do you want to place this memory block to here, or here, or which entry you are going to place this memory block to? The mapping scheme, that is called the mapping scheme, right? So mapping scheme is very simple. Main memory is divided into these cache line sized blocks, and this one is this red box, and blue box is the same size, has the same size as the cache. Okay, so eight memory blocks and 8 cache lines, right? So each entry, each memory block, okay, so let me come back. So first memory block in this red chunk, let's call it chunk. Okay, it is not official name, but it's better to use chunk, blue chunk. Okay. Again, it is not official name, but for explanation purpose. Okay. First memory block in this red chunk always goes to first cache entry, cache entry number 0. Okay, and same thing here. The first memory block in this blue chunk is also goes to first cache entry, entry number 0. Same thing goes to, right, the third chunk, right? Third chunk. The first memory block in this chunk always go to here. Then what is the implication? You know, many different memory blocks could be placed in the same entry, right? Same entry. That means when you bring in memory block to the cache, you need to record location information. Which location this memory block came from. That is obvious, right? So many different candidates. These guys can be placed in the same cache entry. So you have to record that location information here. So then the question is, probably, you know, you would think, okay, then this one is, okay, I have to explain block address first. You know, the data transfer between cache and main memory is based on this memory block, right? Memory block. This whole memory block will be placed into the cache. So it is better to use block address than byte address. Okay. When you talk about cache, it's better to use block address instead of byte address. What is the difference? Simple. The address CPU generate, that is byte address, right? So I have a slide here. That is byte address, right? Main memory. The first byte is located at 0, second byte 1, and so on. Then word address. How do you get word address? In RISC-V CPU, one word is 4 byte, right? So from this byte address, okay, so hexadecimal number, and there is binary number. Okay, so if you represent that hex number to binary, and that is a 1, right? 1 1 0 1 1 1 0 0, right? And so on. So from this byte address, if you ignore last 2 bit, that is word address, right? So that is number. So green one, right? Word address 0. Second word is located at word address 1. Third word is located at word address 2. So how do you get word address? Word address from byte address? Simple. Ignore last 2 bit in byte address. Okay. So then how do you get block address? Simple. This is address, right? CPU generate. Okay, RISC-V is generating 32-bit address. So that is byte address. So how do you get word address? Simple. You ignore last 2 bit. Then that is word address. So how do you get block address? Assuming that cache line size is 16 byte, then you can just ignore last 4 bit. And that is word address. Okay, this one. 3124. That is word address. If block size is 32 bit, 32 byte, then you can ignore last 5 bit. Okay, So address 3125, that is a block address. If block size, okay, or cache line size 64 byte, like Intel smartphone CPU, you can just ignore last 6 bit. Okay, then the remaining how many bits? 32 minus 6, 26 bit will be block address. Okay, so again, because cache access, cache data transfer between cache and main memory is based on block. Okay, so it's better to use block address. Let's use block address. Okay, so here, so this one is block address. So if you want to get byte address, then you can add, we are assuming 8-bit address, right? So we assume also 8-byte memory block, 8-byte cache line. So you can just add three binary numbers, right? Three binary numbers. So 0002 111. It could be. That is, byte address, right? So block address. So let's go back to that question. Okay, you just brought in that memory block to the cache. Then you have to record location information. Location. Where does this memory block come from? Right. So this memory block came from that memory location, this block address. So you would think, okay, then it's okay to probably I can just record that block address 5 zeros. Right? That is simple, right? 5 zeros. I know that memory block came from this one. But probably you can reduce you can reduce the amount of address information you record here because this is hardware, right? If you are able to reduce number of address you record here, location information, you can minimize address information, and still you are able to pinpoint, I know this memory block came from this memory location. That is better. You can reduce the hardware cost, right? So here, so what would be the minimum amount of information you can use from this block address? What would be minimum amount of information you can use to pinpoint the memory location? So you can use just chunk ID, chunk ID. So we, again, unofficial, not official name, right? Chunk, red chunk, blue chunk, black chunk. This chunk ID. How do you get chunk ID? In this chunk, you have how many blocks? 8 blocks. You have 8 cache lines, right? 8 blocks, and that is directly mapped to that cache, right? And these 8 memory blocks are directly mapped to, here, 1-to-1. This one goes to here, second one goes to second entry, third one goes to third entry, and so on. So according to this mapping scheme, probably you don't have to record that whole 5-bit block address, right? Just to record, this upper 2-bit. That is chunk ID. Ignore last 3-bit in block address. Last 3-bit is what? Last 3-bit? That is offset within that chunk, right? Offset, right? First one, 000, first one, 001, second one, 010, third one, and so on. 111, 00, right? That is this one. So here, I don't want to record that whole block address, right? So it is enough to record only chunk ID 00. Okay, I know that memory block came from this red chunk. Let me use red chunk 00. Okay, I know this memory block came from this red chunk. Does it make sense? Right. So that is the one. This figure. So here, many different blocks. Here, second memory block in green chunk, and second memory block in yellow, second in orange purple, all map to same cache line, same cache entry. So when you bring in, for example, this block in yellow, you have to record location information. Then you don't have to record that whole block address. Chunk ID, that chunk ID, right? First 2-bit is enough information to differentiate where it came from. This memory block came from green or yellow or orange purple, right? That's 2-bit. First 2-bit, sorry. So if you mathematically express that that mapping scheme, this is the one. block address, then you can do modular operation. You can do modular operation, right? Number of blocks in cache. How many? In this case, how many blocks? Address, block address. Block address, then block address, right? 8-bit. So 3-bit. So this 8-bit. So 8-bit and 5-bit. This one is block address, right? And then you do modular operation. How many blocks you have in cache? 1, 2, 3, 4, 8, right? So that not 5-bit. Right? So that number block address, which is this 5-bit, then 8. Then you know the location. You know the cache entry. You know the cache entry. This block should be placed to. Right? So if you are able to take a snapshot, of the cache, okay, then cache would be looking like this. Okay, so just one example. Okay, so depending on your application program behavior of your program, think about the sorting program you wrote. Assignment number 2, right? So depending on the behavior, memory access behavior of your sorting program, cache would be looking like this. So interpretation, right? So first cache entry is populated with first memory block in orange chunk. Okay, so I have cache recorded 10, and second cache entry was filled with what? Second memory block in purple chunk. So recorded 11. Okay, 11 purple chunk ID, right? And third cache entry filled with third cache line, this one in green. So recorded 00 chunk ID here. So cache is populated with memory blocks from many different chunks. Okay, does it make sense? So mapping scheme. Okay, mapping scheme. Main memory to main memory block to cache. Then indexing scheme. How do you search? How do you search the cache? That is called indexing. Okay, so same mechanism, indexing. Indexing means you execute memory access instruction, for example, LW. Then based on address, you need to select. Based on address, you have to select cache entry for lookup. Okay. In direct mapped cache, the most simple cache structure, the indexing. Indexing, when you search the cache, you select only one cache entry. So based on this block address, okay, you use, because we have eight entries. You use last 3-bit to select specific cache entry for lookup. Indexing. Okay, you select one cache entry for lookup to search. Okay, to see if the cache has the data I'm looking for. Okay, and then compare that tag information against that chunk ID. Okay, this one and this one. Compare these two. These two are equal, then there's cache hit. Okay, so indexing. Okay, same mechanism, right? Mapping mechanism, indexing mechanism, same mechanism. So okay, so let's move. So so again, direct map cache case. In this simple case, you have data field, okay, tag field and valid field. Valid is just 1-bit information. Okay, so you have let me draw here valid, just 1-bit valid. So at the beginning, when you turn on, if you turn on your computer, valid is all 0, meaning cache has junk, right? Junk information, no data valuable, right? So when you bring in memory block to the cache, then valid bit will be changed to 1. That means this cache entry is valid now. Valid. Okay. So in valid bit tag field and data. Right. So simple cache structure. So one example, 4K byte direct map cache with 1 word memory block. Okay, 1 word, meaning cache line size or block size, memory block size, 4 byte. This is not realistic. Okay, this is not good example, because in real CPU, real processor, 64 byte cache line, 64 byte memory block. But in that example, we are assuming 4 byte cache line, 4 byte memory block. Very bad example actually, because it is not exploiting localities. 2 kinds of localities, right? Temporal locality, spatial locality. What is temporal? You access one memory location, are likely to access same location again and again in the near future, right? Temporal locality. So that is taking advantage of temporal locality, the one word, right? But spatial locality, what is spatial locality? Access one memory location, then very likely to access each neighbor. But this cache is not able to store each neighbor information, right? Because 1 byte, one word, right? 1 word. So very bad example, right? But anyway, let's go through this example. 4K byte direct map cache. Then one have cache capacity 4K byte. Okay, for this cache in 4K byte. Then each one 4 byte cache line. Okay, cache line is 4 byte. So how many cache entries? Number 0, 2, how many? Okay, how many? Simple, right? 4K byte divided this capacity divided by 4 byte. Right? 4 byte. And 10,024. So number 0 to 1023. So you have 1024. So you have 1000. So 0 to 1024. Okay, 4 byte. So 1024. Then how do you search from the address the CPU generate? We are talking about block address, right? So in this case, block is 4 byte. So block address, to get block address from this byte address, just ignore last 2 bit. Right? So ignore last 2 bit, then use next 10 bit to index to search the cache like this. Okay, using next 10 bit to search the cache for lookup and compare tag information against that chunk ID, right? 31 to 12, okay, 20 bit, upper 20 bit in the address. Compare that against the recorded information in tag. Okay, so and then hardware schematic, okay, diagram, and then that information is coming out from the cache, and then that is compared. Tag information, chunk ID is compared against this 20 bit by hardware. If these two are equal and valid is set to 1, valid is 1, then what is this? AND gate. Both are 1, output is 1, AND gate. There's cache hit. And data is supplied to CPU, assuming that CPU is executing LW instruction, memory read. Okay, data is supplied from cache to CPU. All right, any questions so far? Okay, let's go through some example. Okay, is this cache structure taking advantage of what kind of locality? I mentioned two, localities, right? Temporal and spatial locality. So it is taking advantage of only spatial locality. Sorry, not temporal, only a temporal locality. Okay, not spatial locality, because one word, right? It is not storing its neighbor data, so only exploiting temporal locality. So bad cache structure, really bad, right? Okay, let's go through some example. So here we are assuming direct map cache with 8 entry. So direct map cache with 8 entry, index 0. So entry number 0 to entry number 7. Okay, 0 to 7, and cache line size 4 byte. Okay, 4 byte. So again, this is not good example. Okay, 4 byte cache line, 4 byte cache line. And main memory is this, right? So location 24, you have data A, 28 B, and so on. So let's execute these 4 instructions. Okay. This first instruction, read from memory location 24. Okay, A. Second, read data from location 28. This one. And third instruction, store X3 to location 60. So you overwrite, right? See, you overwrite X3. Right? C is gone. And last one, write X4 to location 188. This one. So you are going to overwrite this data. Okay. And for simplicity, let's assume CPU is generating 8-bit address. Again, I don't want to write 32-bit binary numbers, right? That is too long. Right? 32, so 8-bit. How big this cache is then? 8 entry, 4-byte. So cache capacity 32-byte. Super small cache. 32-byte cache. Okay, let's execute the first instruction first. Okay, CPU is executing this LW instruction. So address 24. So in 24, if you write 24 in binary, 8-bit binary, CPU is generating 8-bit address, right? 24, right? 16 and 8. 16 and 8, so 24. So how do you index the cache? How do you search the cache? You need to get block address, right? Block address. To get block address, how many bits you have to ignore? Block size 4-byte, 4-byte block. So you ignore last 2 bit. So we are not going to use last 2 bit, right? Block address. Okay. And then the remaining 6 bit will be used to index the cache. So among these 6 bit, you use next 3 bit to search, select, index the cache entry. So 110, right? 110, 6. So cache entry number 6 is selected for lookup to search. Is it cache hit or miss? Cache contains the information you are looking for, or it does not? It does not, right? Valid bits are all 0, meaning it contains junk information, right? Junk. So cache, we have cache miss. Then what should happen? You have to bring in memory block. You have to bring in memory block to the cache, right? So memory block 4-byte, 4-byte memory block, right? So in our example, so what should happen is that memory block, 4-byte memory block, is placed into the cache. Okay, then you have to record what? Chunk ID. Okay, chunk ID. You don't have to record whole block address, right? So only chunk ID, that 3-bit is recorded. Okay, then valid bit is set to 1. Okay, this entry number 6 is now valid. Remember, this operation is done by hardware. You don't have to worry about that. Software people, don't worry about. Hardware is doing that operation automatically, right? So you have to design that kind of cache controller. Cache controller, hardware will place that memory block to the cache and record chunk ID and set valid bit to 1. Now that entry is valid, right? So first instruction. So then supply that information to CPU. So X1 register will be will contain the data A, right? A, right? X1 A. So first instruction is done. How about second instruction? Read from location 28. So in binary number 28 is this one. Okay, again, indexing. You have to search the cache first. So 111, right? Then cache entry number 7 is selected for lookup. Hit or miss? Miss, right? So valid bit is 0, so miss, cache miss. Then what should happen? Read memory block to the cache, like this. Cache miss, okay? Fill that memory block to that cache entry and record chunk ID, okay? Chunk ID is 000. And set valid bit to 1. Okay, now cache entry number 7 is also valid. That is also valid. Okay, so second, now then supply that data to CPU. So X2 register now contains that data B. Okay, now store word instruction, memory update instruction. This one is a little bit complicated. Okay, please pay attention. This one is a little bit complicated. 60. Update this data to location 60. To location 60. So 60 is this number in binary. Okay, so cache should be searched first. Okay, so 111. Then this cache entry is selected for lookup. So that cache entry is valid, right? So then is it hit or miss? Miss. Why miss? Because chunk ID is different. So that chunk ID, this cache entry is holding data from chunk ID 000. But you are talking about chunk ID 001. So hardware will compare. Hardware, right? Compare that tag information against that 001. So these two are different. So these two are different. Tag does not match, right? Tag does not match. So cache miss. Then what should happen? So what do you think? So that instruction, what is the purpose of that instruction? You want to update memory with X3 data. Okay. So then the question is, do we have to bring in that data into the cache first? What do you think? Let's assume that. Okay. Let's assume. Really confusing. Okay. Let's assume you are going to bring in this memory block to the cache first. Okay. Do we have to bring the block to the cache and write to the cache? Because it is a write operation. Okay. Let's assume that. Let's assume. Bring that memory block to the cache and then update. Okay. Update. That is called write allocation fallacy. Okay. So let me play animation. So that memory block will be placed. Okay. So go back. So that cache entry will be replaced with a new memory block. Okay, new memory block from location 60. Okay, so that information will be replaced with C, and then record that chunk ID 001. Okay, and still valid. Now is valid, right? Then it is not, we are not done yet. You just brought in that data, that memory block to the cache. Purpose of store instruction is what? Update memory, right? Update. We haven't updated memory yet or cache yet, right? So now we have to write new value to new value. What is new value? X3. New value to that memory location. Okay. So then the question is, do we have to update only cache or both cache and main memory? Two choices, right? First choice, update only cache. Second choice, update both cache and main memory. And the bottom line is that instruction, this instruction is what? Update main memory, right? That is the purpose. Update memory location 60 with that data. Okay? That is the purpose of that instruction. So eventually, you have to update main memory. That is for sure. But for now, let's update only cache. And main memory will be updated later on. The reason is, what is the reason? Because main memory is so slow. I don't want to touch main memory, if possible. Okay. So I don't want to touch main memory. Okay. And I want to play with only cache. And main memory is so slow. I don't want to touch main memory. Right. So that is why. Okay. For now, I'm going to update only cache. And main memory will be updated later on. Okay, don't worry. Okay, cache says, okay, don't worry, I'll update main memory later on. Okay, with new data. Okay, for now, I'm going to update only cache. Okay, so let's assume, okay, this one. And this one is called write back policy. Write back means cache will be updated only. Okay, and the other policy is called write through. We will talk about that. Write through. Right? Through means, not only cache, but main memory. So both cache and main memory will be updated. Right? That is write through policy. But I don't like write through policy because main memory is so slow. I don't want to touch. Updating main memory is taking time. Right? I don't want to do that. Right? Anyway, that is called write back policy. Only update cache. So that means cache contains new information. Main memory has old information that should be updated with that X3. Then how do you know? By looking at this cache. How do you know? Cache has the latest information and main memory has old information. How do you know? How can you tell? You cannot tell by looking at this, right? So you need additional. How do you know? Sorry about this. So how do you know which block in cache need to be, which block in cache should be written back to main memory later on. So by looking at this, you cannot tell. So we need additional bit. Okay, that is called dirty bit. Okay, so when you update cache, when you write to cache, you have to set this bit to 1, dirty. Dirty means this cache entry has new information. And that information will be eventually updated to main memory. Okay, dirty bit. So by looking at this dirty bit, you can tell, okay, that entry should be updated to main memory later on. Okay, does it make sense? A little bit confusing, right? So I mentioned 2 different policy, right? A little bit confusing, right? Write, allocate. Okay, first one, second, write back. Okay, so write allocation means when you write operation, meaning CPU is executing store instruction, memory update instruction, store like SW, SH, or SB in RISC-V, right? Store instruction. So you search the cache, then cache miss happens. Cache does not have the information. Then what should happen? Do you want to bring in new data? Allocate. you want to allocate that memory block to the cache first, or do not allocate? So, right, allocation policy means when cache miss happens, okay, I'm going to allocate that memory block to the cache first. Then write back means what? When you update. So this one, when upon miss, when cache miss happens, allocate first. This one, when write, upon write. When you update, do you want to update only cache or both cache and main memory? So write back means, okay, I'm going to update only cache. Okay, and set dirty bit to 1. Two different things. Two different allocation. When you miss the cache, okay, allocate this block to the cache. When you update, okay, I now this cache contains the memory block. Okay, write allocation, allocate it. And write back means, okay, I'm going to update only cache. Okay, cache. Two different policy. So okay, so that is the information. Now, last instruction, memory update instruction to location 188. So 188 is this number in binary. Okay, and then you need to search the cache first, right? So this one is a little bit also complicated. 111. So you are searching cache entry number 7. Hit or miss? Miss. Why? Because chunk ID, this memory block, right? This memory block came from location 60. This memory block, right? So 001. But you are looking for what? This chunk ID 101. So by comparing these two are not equal, right? So we have cache miss. Then what should happen? We are talking about write allocation policy and write back policy allocation. But so then the thing is you have to use that cache entry. But this one says dirty. This cache line is dirty, meaning you have to update main memory with that data. So before you use cache entry, you have to update main memory first. Before you replace, okay? Before you remove this data, you have to update first, right? Because dirty cache miss. Dirty bit is set. Dirty bit is set, so you have to update main memory. Okay. Now then you are safe to use that cache entry because I updated, right? Updated location 60 with data. Okay. So now according to write allocation policy, okay, bring in that memory block to the cache. Okay. Then record chunk ID to tag 101 and valid bit is 1. Okay. This entry is valid. Okay. Then what should happen? What should happen is according to write back policy, data should be this data x4 should be written to cache line. So now cache has a new information and main memory has old information. Okay, so that information will be eventually updated to main memory because that instruction, memory update instruction, right? Store word instruction, not cache update instruction, memory update instruction. Cache is the memory component, right? memory component in between these two to speed up execution time only, right? Speed up execution time, right? Okay, does it make sense? Any questions so far? Okay, now let's talk some more about these two policies. Right? A little bit confusing. Okay, so this one, Dong, can you please?
Can you hear me?
Mhm.
Handling writes. When it comes to a read miss, we bring the block to cache and supply data to CPU. When it comes to a write miss, there are options you can choose from upon a write miss. Write allocate, bring the block into cache and write. And write no allocate is write directly to main memory. Um, is this write operation? Oh, so bringing the block to the cache.
Oh, without this one, without.
Without, okay.
Okay.
Maybe without bringing the block to the cache. And when writing, write back, update values only to the blocks in the cache and write the modified blocks to memory or the lower level of the hierarchy when the block is replaced. Write through, update both the cache and the lower level of the memory hierarchy. Write allocate is usually associated with write back policy. Write no allocate is usually associated with write through policy.
Okay, thanks. No, handling right. We are going to talk about these four different policies. Before that, cache is accessed. Cache is accessed when CPU execute memory access instructions. Memory access instructions, LW or SW, right? So CPU execute memory access instruction, memory read, and memory write, right? Then cache will be checked first. Okay. For read operation things is very simple, right? Things are very simple, right? You miss the cache, then bring in, right? Bring in memory block to the cache, then supply the data to CPU. Simple. But write operation a little bit complicated, right? Write operation. So when CPU execute store word instruction, memory update instruction, you miss the cache, then what should happen? Okay, first one. When you miss the cache, you are executing SW instruction, memory write instruction, then you miss the cache. Cache does not contain the information you are looking for. Then what should happen? Two different policies. Allocate or no allocate policy, right? Allocate. Okay, allocate means, as the name says, allocate. Allocate, right? Memory block to the cache. No allocate, right? I'm not going to allocate, right? I'm not going to copy the memory block to the cache. No allocation, right? So upon miss, when you have a miss, cache miss, write miss, two different policy. Okay, allocate, no allocate. And when you actually write, memory update, right? You have to write data. Two different policies. Write back means, okay, I'm going to update only cache, update, write back. Write through means both these two guys, these two, cache and main memory, right? So then, there are four different combination, right? Write allocation, write no allocation. So then write back, cache, write through. Okay, write back and write through. So four different combinations. But in reality, two combinations are mostly used, right? Allocation and write back. First one, and write no allocation and write through. That is typically used. The other two are not used in reality, right? Allocation, write back. Okay? Right, allocation, write back. Right? Right, no allocation and write through policy. So let me explain these two. These two combination with example. Here we are assuming we are assuming, I think 1208, 1208, okay. We are assuming CPU is executing two instructions, toward instructions. Let me hook up X6. The location, let me use 1208 hex. Location 4. Right? So CPU is trying to write this data to location 1208 and location 4. Okay, let's go back to the beginning. Okay, so that is the initial state. Okay, so we have what? Okay, here. Okay, cache first. This cache, cache line size 16 byte. Okay, 16 byte cache line size. Realistic, right? It is exploiting both temporal locality and spatial locality. Right? So 16 byte, 4 words, right? In other words. So main memory should be divided into these 16 byte blocks, right? 16 byte blocks. So location 1208. Okay, 1208. 1208, this one. 1208, that is the memory block. There is a memory block containing data in 1208. And this one, 04, this one, the first one. This is the memory block, right? Memory block. Okay, so let's execute. Then now we are assuming cache contains memory block from the contain memory block, that memory block. Okay, that is the initial state. Okay, again here 5, 6, 7, 8. Cache has memory block, this memory block. Okay, so that memory block and chunk ID and valid bit is set to 1. Okay, that is assumption. Okay, state, initial state. Then let's execute. First, memory access, store the instruction. CPU generate address and based on indexing scheme, and that cache entry will be selected for lookup. And then chunk ID and these two are equal. So we have cache hit. Then what should happen? Write hit, right? Store the instruction, cache hit. What kind of hit? Write hit, not read hit, write hit. What should happen? You don't have to worry about allocation, no allocation policy, because that is applied if you miss the cache. So we have a cache hit, right? So now write back policy, this one, right? Allocation, write back policy. So write back means cache will be updated only. Right? So data, assuming X5 contains 1, 2, 3, 4, 5, 6, 7, 8. Okay, the data will be written. Data will be written to the cache. Okay, only cache. So the ultimate is set to 1. Okay, the ultimate is set to 1. Then main memory will be updated eventually by the cache. So you don't have to worry about, right? That will be data will be updated. So first instruction is done. Now second instruction. Okay, update this data to location 4. Then assume that it happens to index. It happens to select that cache entry. Then we have cache miss. Cache miss, write miss. Then write allocation policy, right? So you have to bring in memory block, the first memory block. So 1, 2, 3, 4. So allocate memory block first, okay, like this. Okay, 2, 3, 4, 1. Then record chunk ID, right? Chunk ID. Then set validity to 1, and dirty bit is not set. Okay, so go back. So we just allocated memory block to the cache. Okay, then you have to update write operation, do write operation. So the data assume that X3 contains all the 80s. Okay. Then update that particular word. Okay, because location 4, right? Location 4 is this location 2, right? So update this one and set dirty bit to 1. Okay, write back policy, only update cache. So write allocation and write back combination. So how about write no allocation? Right, no allocation and write through policy. So how's it different from the first combination? So let's execute these two instructions. So same, right? There is initial state. Okay, initial state. Then that is selected for lookup, and we have cache hit. What should happen? So we are talking about we have cache hit. So write through policy. According to write through policy, update both cache and main memory. Okay, update both these two guys. Okay, so we don't have dirty bit in write through cache. Okay, because main memory will be updated all the time. Okay? Both cache and main memory. Okay? And second toward instruction, it happens to select index this cache entry for lookup. Then cache does not contain valid information. We have cache miss. What should happen? Right? No allocation policy. Do not allocate. Do not bring in memory block. Okay. And then write through. So do not allocate. I'm not allocating. Cache does not contain the memory block. So update only cache. Oh, sorry, update only main memory. Okay, like this. Does it make sense? Any question? Okay, let's move on. Okay, this one. Eugene?
Read hits. This is what we want. Read misses. Store the CPU, fetch the corresponding block from memory, deliver it to cache and CPU, and continue to run CPU.
Okay, please stop there. Let me explain first. Read operation, write operation. Again, cache is accessed when CPU execute LW memory read instruction or memory write instruction. Right? Memory read, write instruction. Right? So read hit means what? Based on address, CPU generate read operation, right? Read operate based on the address CPU generate. You search, you select one particular cache entry for lookup, right? Compare tag information against that the corresponding chunk ID field, right? So compare these two, equal, then cache hit. Okay, so read hit. That is what we want, right? Read hit, then cache is able to supply data to CPU directly. So it is going to be very fast. Okay. So I have to. Okay. Okay. So that is read hit. How about read miss? Read miss, same, right? You select particular cache entry for lookup, but this guy does not contain the information you are looking for. Then cache miss. Then you have to bring in, right? Bring in memory block, then supply the data to CPU. So if you draw pipeline execution diagram, it looks like this: patch, right? Decoding, execution, memory access, but you have cache miss. So you have to store the pipe. Store the pipe. Then probably, I don't know, depending on memory access latency, then miss penalty, right? So let's say it is 100 clock cycles. Then store the pipe for 100 clock cycles, then write back, right? Store the CPU, store, right? Store the CPU, fetch corresponding block from main memory and deliver to the cache and CPU. Okay, then write back, continue to run. So that is pipeline execution diagram. You have to stop the pipe, right? Eugene, can you please? So these two.
Write hits, write through cache, write data to both cache and memory. Write back cache, write the data only into the cache and set the dirty bit. And write the block to memory later when replaced. Write misses, write allocate with write back. Read the block into the cache, then write the word only to the cache. Write no allocated with write through. Write the word only to the main memory.
Memory without bringing the block to the cache. Okay, thanks. Write hit first. Write hit, right? You are executing store instruction. Store instruction, then index the cache. Cache contains the valid information. Okay, valid and the information you are looking for. Then update, depending on the policy, right? Through policy, update both cache and main memory, right? In case of write back policy, update only cache. Okay, main memory will be updated later on by hardware. You don't have to worry about dirty bit set, right? So cache will update main memory eventually. Right? So write miss, it is complicating, right? Write miss. Okay, search the cache. Cache does not contain the information you are looking for. Then that policy, allocate with write back. Allocate, right? Memory block allocation first, then update only cache, write back, right? No allocation. Okay, I'm not going to bring in. Okay, that I'm not going to bring in. I'm not going to do this, right? So according to write through policy, main memory, because cache does not have memory block, right? Cache does not have main memory will be updated, right through. Okay, there's one. Okay, so some realistic cache structure. So here, 4K by cache. 4K by cache with 16 byte cache line size. 16 byte cache line size. Then how many cache entries you have? How many entries? Simple, right? 4K byte divided by cache line size, right? 16 byte. 256. Right, 256, right? Entry number 0 to entry number 255, right? So you have 256, okay, opposites, 0 to 255, right? Cache entries, then block address, right? So again, because cache access is based on block address, right? So what is block address? You're talking about 16 byte block size, 16 byte. That means you ignore last 4 bit. Last 4 bit from the address. Then the remaining 28 bit is block address. Okay, so based on block address, you have to index the cache. So which one is used to index the cache? Because we have 256 entries, you use 8-bit. Next 8-bit to select cache entry for lookup. Then that information is coming out. That information is coming out from the cache, and that is compared. Okay, that is compared against chunk ID. Okay, chunk ID, this one, tag information. So these two are equal. These two, tag and chunk ID, these two are equal, and valid is set to 1. Okay, meaning AND gate, right? Both are 1, both inputs are 1. Then output is 1, meaning cache hit. Okay, then there are four data, right? So among these 4 data, the only one is the one you are looking for, right? LW instruction, LW, right? Load word. Right? So reading data, 1 data, right? 4 byte. So then you have to select 1 out of these 4, right? So the data is coming out, going through multiplexer, right? Multiplexer, then multiplexer means you need to have selection signal, right? Someone should select. Who is providing the selection? Control logic? No, right? From this address, right? From this address, 2-bit. Okay, so 2-bit is used to select the word you are looking for. Okay, and that is supplied to CPU. Right? Address, right? So based on that address, 2-bit is used to select particular the word, right? 4 words, then select 1. Right? That is a rough schematic diagram of cache and search logic. Search, right? Search, then select the data you are looking for. Does it make sense? So this cache is taking advantage of both temporal and spatial locality, right? Because cache line size 16 byte. Okay, so temporal locality, you access one location, then next time you access same location again and again. Okay, each neighbor data also, right? Spatial locality, you access this location, then very likely to access each neighbor, right? Each neighbor. So exploiting both temporal and spatial localities. Okay, I guess time is almost up. It's better to stop here, I guess. Any question before letting you go? Okay, that is for today. And see you. I'll see you next time. Bye.
Thank you, Professor.